This is chapter 6, problem number 27. The lucky number for this problem is 9. A spring has a spring constant K. All right, what is a spring? A spring is a metal coil. Well, it can be other material, but it's coil-like material like this. When you apply force on it, if you hang weight on it, it's going to stretch to this one, okay? Or if you compress it, it can move, you can squeeze if you compress it this way. This is called a spring. The length that it elongates actually proportional to the weight that is hanging on it. For example, if you put 1 kg, it will be over here. Then if you put 2 kg, then it's going to extend. Let's say this is delta x. Over here, it will be delta x over here, and over here will be another delta x. Okay, so the elongation is proportional to the force that is acting on this spring. How do we write it mathematically? When we say the force is proportional to the elongation, so force is proportional to elongation, let's say delta x. So if they are linear, then I can say force is equal to a constant times delta x. And we call this constant a spring constant. If this number is high, that means when you want to change a little bit, when you try to elongate a little bit about this spring, you need to put a lot of force. That's why based on this spring constant, we know whether the spring is very stiff or very easy to stretch. Okay. So I'm going to write down 2 very important formula. This is the first one. So for a spring, and it's called the Hooke's law, by the way, that is equal to force is equal to spring constant times delta x, where delta x is elongation. Before, when we say work is equal to force times distance or elongation. So if you try to apply force here, try to move from A to B, let's say it's the same distance from B to C over here, you are going to spend different amount of work or energy. Why? Because from A to B, you spend very little force, where from B to C, you spend more force, although the distance is the same, but the force is different because you stretched the spring more. And therefore, the work or the energy that you store in the spring, so this is another potential energy. Before we have seen potential energy due to gravity. So this one is potential energy due to a spring that is equal to half times K times delta x square. Once again, K is a spring constant. If K is bigger, then the spring is stiffer. Okay, so we know the spring constant, how much this spring must be compressed to store that energy. Okay, so energy of a spring is equal to, potential energy of a spring is equal to half times K times delta x square. And by the way, let's look at the unit. Okay, so over here, potential energy have the unit of joule. Over here, delta x is meters. So what would be the constant? Okay, so this one must, so over here, meter square. So this one, K must have the constant of, you can have 2 ways of looking at it. It must be joules per meter square. Okay, or if you look at this one is Newton, this one is meter, so this K must be Newton per meter. They're the same, Newton per meter. Okay, all right, let's get back to this problem. And by the way, the lucky number for this problem is 9. 9, that would be the lucky number. All right, so this one, potential energy is 45 joule. is equal to half times spring constant is 88, okay, times delta x squared. Okay, so we can solve for x. How do we solve it? We multiply both sides by 2 and then divide it by 88. So 45 multiplied by 2 divided by 88 and take a square root of it. Square root of second answer. Okay, what I get is x is roughly equal to 1.01 meter.